Hello everyone, welcome to the Mercury Virtual. Hope you are doing good. Today I am going to continue with your chapter number 8, that is exceptional control flow. In the last class we have discussed what is the process and how different processes will work. Now today I am going to start with the next topic, that is your process control. So this is the topic of the today's class. This is process control. This says Unix provides a number of system calls for manipulating processes from C program. That is, Unix provides, or the operating system provides, a number of system calls. That is, a number of system calls is available for manipulating the processes, for arranging the processes from the C programs. This section describes the important function and give examples of how they are used. So process control means a method that is provided by the system call for manipulating the processes. This is our topic, but before this, let's take a quick review what we have covered in the last class. In the last class we have discussed, or we have started with the chapter number 8 continued, that is exception control flow. We have discussed different types of exceptions. One is your reset, one is your interrupt, one is your exceptions. And we also discussed the terminologies that is used in the exception. So exception is a condition that causes the processor, or that makes the processor to escape from the normal condition. Because at the for example, at the normal condition, the CPU is executing its command. So whenever it escapes from the, or whenever the processor is escape from the normal control flow, from the normal conditions to a predefined location to deal with the condition, that is known as an exception. So exception is an unusual condition that occurs that makes the processor to escape from the normal control flow. And these are the types of the exceptions. One is reset, that is external. One is interrupt, that is also a part of the external. One is exception, that is internal to the processor. One is software interrupt, that is also internal to the processor. So these are the four types of exceptions that is used in the computer or compiler design. Then these are the exception types. One is reset, that is external, that is asynchronous to the internal processing. Why it is known as asynchronous? Because it is not synchronized with the processor. It is non-synchronized, that is asynchronous to the internal processing. Then we also discuss about the interrupt, that is also the external, that is also asynchronous to the internal processing. Exception, that is also internal, that is internal, not also, because first about two, that is reset and the interrupt, are the external, but exception is internal. That is, for example, divide by 0 gives the exception, that is the internal part. Then we also discuss about the software interrupt, that is what is the software interrupt, why we are using the software interrupt. That is also internal, that is associated with the special instruction known as the software interrupt. Then we also discuss about the interrupt and the reset. This is a diagram that shows the interrupt, that shows the reset. So this is the processor core. Then there is a reset. Then there is an interrupt controller. various interrupt sources. So these are the various interrupt sources: interrupt 1, interrupt 2, interrupt 3. There is an interrupt controller that controls the interrupt. Then at last it goes to the processor, that is in form of interrupt. Then we also discuss about the two types of exceptions, that is interrupt and the traps. So we have discussed about the interrupt that is caused by the external events. External events includes the network, the keyboard, the disk input output, and the timer. And this also includes a page fault, that is a part of the virtual memory system call, that is user request for the OS function or OS action. Then we also discuss about the detail what is an interrupt, that is asynchronous or synchronous, that may be suspended or resume the user program. Then we also discuss in detail what is a trap, that is the internal part that is caused by the internal events. That is a part of the exception condition, that is overflow, undefined instruction, hardware malfunctioning, that is synchronous to the program execution. So this is very important, that which exception is in internal, which exception is external, which exception is synchronous, which is asynchronous. Then we have discussed about the next topic. One topic is types of exceptions, that we have discussed with the help of book, with the help of PPTs. Then the next topic we have discussed in the last class is processes. That is what is the process and how the process will be executed, created, and destroyed. Today's topic is continued to the process only, that is a process control. So it is very better, or it is very useful to get the knowledge of the process that we have discussed in the last class. This is the definition. A process is an instance of a running program. Instance means it is an overview, it is an example of the running program. That is your definition. Then it's one of the most profound ideas in the computer science. That is, it is one of the most profound idea in a computer science, not the same as a program or the processor. That is, process is not same as the program. Why? Because in simple terms, process is a program in execution. Whenever any program is in execution phase, is in studies phase, that is known as the process. So it is not similar to the program or the processor. Then we also discuss about the process that provides the each program with the two main or the two key abstractions, that is logical control flow and the private address space. Then we have discussed how these are maintained, or how these two abstractions or the key abstractions are maintained in the program, in the process. That is your two key abstractions, that is a part of the logical control flow and the private address space. Then we also discuss about the logical control flow that makes the process, that each process has its own logical control flow, that is a part of the process A, process B, and the process C. So this is the diagram that shows the logical control flow. Then we also discuss about the concurrent processes. That is, what is a concurrent process? So whenever two processes lies, or two processes are executing, or two processes are executing, run concurrently, that is at the same time, then that process is known as a concurrent process. One more condition is that concurrent process flow always overlap in time. That is, they overlap with each other. Processes will overlap with each other. Examples includes by this diagram, concurrent processes are process A and B, process A and C. Because you see, this is a line that is the same time is used by the A, same time is used by the B. In the same way, same time is used by the A, same time is used by the B. But there is no comparison, there is no time overlap between the B and the C. That is your sequential process, that is B and the C. Then we also discuss about the user view of the concurrent processes. That is, what are the user view, or how user views the concurrent processes. Then we have discussed about the context switching. That is, what is the context switching? That is simple terms, when the OS manage, or when the OS manage the switching technique, that is share the part of the, or divide the main process into multiple parts, that is managed by the, or that is managed by the operating system, that is known as the kernel. Kernel is not a separate process, but it is a part of the only user process. This diagram shows how context switching mode can change from one code to the another. One is user code, one is kernel code. Again user code, kernel code. One a user code is converted into or going into the kernel code. Another user code is going to the kernel code. Then we also discuss about the private address space. That is your next abstraction. That is your next key abstraction. That is your private address space. This says each process has its own private address space. This is the diagram that shows the private address space, or how one process lies in the address. That is your multiple parts of the address. So first of all, there is the area that is of kernel and the virtual memory, then user stack, then ESP, that is a stack pointer, then there is a blank area, then again memory map region for the shared libraries, then again the break, that is your blank area, then runtime heap, that is managed by the malloc function for dynamically allocates the memory, then read write segment, and then again read segment, that is only read only segment, then again unused data or unused table. Then we also discuss about the system call, that is a programming hint, that is if there is any error it returns a -1, otherwise it gives the or uses the function that is the str error function that tells the error number. What is the error number? Then we will discuss multiple examples by str error number or str error function to display the code, that is your str error. Then we will discuss about the multiple codes, that is example, that is PID, that is a process ID T fork. Then we also discuss how to create the new process with the help of the fork. This is the example that shows how to create a new process that is identical to the calling process. That is, we are creating the child process that is very identical, very similar to the calling process, that is your parent process. So one is called function or the called process, that is a child process. One is calling process, that is your parent process. Return 0 to the child process, return child PID to the parent process. This shows fork is used to create the new process in the compiler design. Then we will discuss about the example, that is a fork example. Then we will discuss about the possible outcomes. These are the possible outcomes that we have discussed. This is the example that we have discussed. There is L0, L1, L2, bye-bye. This is what we have discussed in the last class. Again, we also discuss about the new concept, that is your exit, that is your destroy process. How to destroy? By using the function that is your exit function. So this is what we have covered in the now. Let's start with the today's topic, that is your process control. Now, till now we have discussed what is a process, how process will be created, how fork will be used. Now, next target is that, next motto is that, next topic is that, how to control such processes. Suppose I have created one topic, one process, that is by using the fork, by using the PID, we have created one process. Then how to manage? How to manage means how to control different processes, that is your process control. Now, this says Unix provides a number of system calls, that is with the help of system call, the process will be controlled, that is provided by the operating system for manipulating the processes from the C programs. This section describes the important function, that is the following chapter or the following topics describe the process control or the important functions and give examples of how they are used, that is how they are used and why they are used and to whom it will be used. Now let's see what are the different functions. Now 4.1 is obtaining the process ID. that is how to obtain the process ID, is one of the function, one of the manipulating process that is used in the process control. That is obtaining the process ID, that is how to obtain the process ID, that is a unique ID for every process. This says every process has a unique positive process ID, that is every process has a unique means that is not similar to anyone, and it is also a positive process ID, that is a PID. The get PID function returns the PID of the calling function. That is, this is a function that is used to return the PID. Suppose I want the PID of a process, then I will use the PID function on, sorry, then I will use the get PID function so that I know what is a PID or what is the unique number for the process, for the calling process. The get PID function returns the PID of its parent, that is get PPID. One is get PID, that is used for getting the process ID for the child process. One is get PPID, that is your parent ID, parent process ID, or the process parent ID, that returns the PID of the parent process, that is your calling process. So before this, let's take, or you have understood that what is a, one is a calling process, one is a called process. Calling process is used for the parent process from which a new process is derived, that is known as the called process or the child process. So one is child, that is a called process, one is calling, that is a parent process, right? So whenever we get the, or whenever we obtain the process ID of the parent, we use the get PPID. Whenever we want the PID of the child, then we use the get PID. This is an example that shows PID underscore T get PID void, PID underscore T get PPID void, returns PID of either the caller or the parent. This says the get PID or the get PPID routines returns an integer value of type PID underscore T. That is, it returns an integer value that is a positive integer value of the PID underscore T, which on the Linux system is defined in the type.h as an integer. So it is defined in this header file, that is types.h. Then next function or next technology that is used for controlling the process is how to create and how to terminate the processes. This from the programmer perspective, we can think of a process as being in one of the three states. That is, if the process has created, then it is available in three states, or it is available in three methods, that is running, stop, terminate. So one is used for the, that is used that one process is created by using a function, that is a function, and it is terminating by using the exit function. As I told you in the last class, one is fork, one is exit. It is available in the three states. One is running, one is stop, one is terminated. So running process, the process is either executing on the CPU or is waiting to be executed and will eventually be scheduled by the kernel. That is, it is executing by the CPU on the CPU or waiting to be scheduled by the kernel, or it wait for the kernel to be scheduled. That is it, running status. Either it is currently running or it is waiting for the next schedule. That is a running status. Then stop, that is the execution of the process is suspended and will not be scheduled. That is, once a process has finished execution or there is some error, then it stops the execution. Then it stops the execution. Now it's okay. Then the execution of the process is suspended and will not be scheduled. That is, once the execution of the process is suspended, that is it is not used or suspend, then it will not be rescheduled. That is your stopped criteria, stop state. This says a process stops as a result of receiving these signals. That is, if these signals are received, then the process will be stopped. The signals are signal, that is your SIG stop, SIG TSTP, SIG TTIN, or SIG TTOU signals, and it remains stopped until it receives a signal continued signal. So these are the multiple signals that is received when the process stopped, and this is the only signal that is used until, or that is process will execute or process will in running state when the signal received, that is the signal continued, at which point it can begin running again. Now this says a signal is a form of software interrupt that will be described in detail in section number 5. That is your next topic, that is your tomorrow's topic in detail. What is a signal? In simple terms, signal is a part of the software interrupt by which we can communicate with each other. So we have discussed about the running state, we have discussed about the stop state. Then terminated, that is in stop the process is not terminated fully, that is permanently, it is stopped on a temporary basis. But in terminated phase, that is the process is stopped permanently. A process becomes terminated for one of the three reasons, that is it becomes terminated by three reasons. One is receiving a signal whose default action is to terminate the process. That is, it receives a signal, it receives a line, and that is whose default action, whose default means predefined action is to terminate the process, or it returning from the main routine, that is the process is returned from the main routine, or it is called from the or calling from the exit function, or it is calling the exit function. These are the three states that is available for creating and terminating the process. This is the example for destroying, that is void exit int status. This function does not return, it will be terminated. The exit function terminates the process with the exit status of the status. A parent process creates a new running child process by calling the fork function. So there are two functions that is used for creating and for terminating. For creating, it is used as a fork function, and for terminating, it is used for the with the help of the exit function. This is the example of the fork function for creating the process, for creating the child process, that is PID underscore T fork void, that is returns 0 to the child, PID of the child to the parent, minus 1 on the error. This is the example that we have discussed in the last class also. The newly created child process is almost but not unique identical to the parent. That is, it is identical or similar to the parent process. The child gets an identical but separate copy of the parent user level virtual address space. That is, even though it is similar to the parent, but it is identical, or it receives an identical copy of the parent's user level virtual address space, including the text, data, and BSS segments. The child also gets identical copies of any of the parent open file descriptors, which means that the child can read or write any file that were open in the parent process by when it is called fork. That is, if a new process is built from the parent process, then the child process gets all the responsibilities, get all the files from the parent process and do the needful things that he or she will, or that it will do. The most significant difference between the parent and the newly child process is that they have a different PIDs. That's why I'm saying they're identical, but they're separate. By why they are separate? By using the different PIDs. The fork function is interesting because it is called once but it returns twice. That is, it is very interesting but confusing. Why it is confusing? Because it is called only once but it returns the twice value. That is 2 times. Once in a calling function, once in a newly child process. In the parent process, the fork returns the PID of the child In the child process, fork returns the value of the 0. So this is fork returns the two values. In the parent, it returns the PID of the child. In the child, it returns the value of the 0. Since the PID of the child is always non-zero, the return value provides an unambiguous way to tell whether the program is executing in the parent or the child. This is the example. There are some subtle aspects to this simple example. That is, it calls the ones, returns the 0. So let's take what is the example or what is the figure saying. That shows a simple example of a parent process that uses fork to create a child process. When the fork call returns in line 8, x has a value of 1 in both the parent and the child. That is, when the fork returns a line or returns a value 8, then x has a value of 1 in both the parent and the child condition. But the child increment and prints its copy of x in line 10. Similarly, the parent decrements and prints its copy of x in line 15. That is, the child increment and the parent increment, and the child reaches to the line 10 and the parent reaches to the line 15. When we run the program on the Unix system, we get the following output. That is, parent becomes 0. Why parent becomes 0? Because it will be decremented one by one. And why child becomes 2? Because it will be incremented one by one. That is, x equals to 0 in child, x equal to 0 in parent, and x equals to 2 in child. Now, there are some subtle aspects that is used in this example. One says call once, return twice. That is, fork function that is used for creating the process is called once by the parent, but it will return the two values, that is the twice values, one to the parent, one to the newly created child. That is, the one function is used, or one part is used for the parent and one is used for the newly created process, or it returns for the two parts, one for the parent, one for the newly created child. This is the straightforward for the program that creates a single child. Then next is your concurrent execution. That is, more than one process are executing at the same time. That is your concurrent execution. Why? Because the parent and the child are separate processes that run concurrently. The instructions in their logical control flow can be interleaved by the kernel in an arbitrary way. These are the subtle aspects. That is, concurrent execution is also available in the parent-child process that is created by the fork process, that is created by the fork function. The next subtle or next aspect is that this is the example. First of all, there is a header file that is defined, that is csapp, that is application.s, then int main PID underscore T PID, that is PID is declared, that is a variable is declared, that is of PID. Then x equals to 1, that is 1 is initialized to the x and that is of int type. Then PID equals to 4. Then for function is used for creating the process that is stored in the PID, that is the outcome of the fork is stored in the PID. Now, if PID equals to 0, that is, if it is a child process, then printf child x equals to plus x, that is x equals to %d, that is the category of the value of the child, then incrementing the x value, then exit 0. Exit 0 means terminate the process. Then next is your printf for the parent process. Parent x equals to n minus x. This is used for incrementing the values of x, and this is used for decrementing the values of x. Then there is a exit 0. This is the example that shows using fork to create a new process. That is how fork is used in the parent process and the child process to create the new process. That is from the child to the parent or from parent to the child. Next subtle is that duplicate but separate address spaces. So this is duplicate part, that is the same address space is used, or the same value is used by the parent as well as the child process. But the main thing is that the main criteria is that they have a separate address space. That is, they are stored at the different places. So they have a different address space. If we could hold the parent and the child immediately after the fork function returned in each process, we would see that the address space of each process is identical. So how they are separate, how they are unique with one another? Why? The main thing is that they have a separate PID, that is a process ID. Each process has the same user stack, the same local variable value, the same heap, the same global values, and the same code. So they have a same variable, same memory, same heap, but they have a different unique ID. That is your different or the unique PIDs. Then next subtle is that they have a shared files. When we run the sample program, example program, we notice that both the parent and the child print their output on the screen. The result or the reason is that the child inherit all the parent open file. That is, the child gets all the open or all the child in parent open file. That is, child gets inherited the files from the parent. When the parent calls fork function, that is, the parent calls a fork function. Why? For creating a new process, the stdout file or the stdout file, that is a standard output file, is open and directed to the screen. The child inherits this file and thus its output is also directed on the screen. So there is a shared file, there is a duplicate, there is a single file but returns the two values. So these are the various subtitles when we use the create function, when we use the fork function to create a process, and the exit function to terminate the process. One more thing, the fork function is also useful to sketch the process graph, where each horizontal arrow corresponds to the process that executes instruction from the left to the right, and the vertical rows correspond to execution of a fork function. Now, for example, how many lines of output with the program in 16A and 16B will provide? This is called function once, this is called fork twice, that is, this is called only once, this is called twice, this is 3 times. These are the examples of the fork function and their graphs. So this is call or the calls fork once, that is, it calls for the one part, or it calls for only once, that is a call once. This is include hash include csapp.h. So this is the header file that includes the basic function that is used in this file. Then int main, getting the main function, or starting with the main function, it has a return 0. That's why we are using the int. Then we have called the function that is a fork function only once. Then uses the printf, that is a hello. Then use the exit function, that is return the 0. So first of all, fork is called, then hello world is written, then exit 0. Now let's see. This says prints 2 output line, that is, it prints the 2 output line. Why? One time fork is used, one time it is used by the parent, one time it is used by the or inherited by the child. So it is run or prints the 2 output line, that is, only one function gives the 2 output line, one for the parent and one for the child, that is hello hello. Then next calls fork twice, that is, it calls the twice. So there is one fork, there is another fork, that is csapp.h fork, then printf hello. So one fork is used for the 2 hellos, one fork is used for the 2 hellos. So in the same way, the fork is used twice. So one fork is used for the parent and the child both, one fork is used for the parent and the child both, another fork is also used for the parent and the child both. There are 8 output lines. This is one fork, this is one fork, this is one fork. That is used by the another function also. These are the graphs that is available for the fork function. This says it creates a process when it executes the first fork in the program. Each of these calls printf1, so the program prints two output lines. That is, each of them, these means one is a child, one is a process. Now, but if you are able to fork twice, that is, we have seen in the fork process to create a child, then the parent and the child for each fork result in two more processes. The same example that we have discussed. This is the next example, that is the 3 times fork. Then next is this is the example for your practice. Then next topic for the controlling or the for the process control is reaping the child processes. That is how to reap the child processes. This says when a process terminates for any reason, that is the process terminate with any reason, with any criteria by terminate for any reason by using the exit function, the kernel does not remove it from the system immediately. The part of the operating system that is kernel does not remove, that is does not vanish the reap child process from the system immediately. Instead, or rather than, the process is kept around in a terminated state until it is reaped by the or by its parent. So on the other hand, the process is kept around in a terminated state. It is not removed permanently or immediately. It is kept around in a terminated state until it is reaped by the parent. So this is the most important point. Whenever the process gets terminated, it will not remove, but it is removed by the parent or reaped by the parent on a later stage. Why? Because sometimes there is a condition that I want the process again. So it is better to keep the process in a terminated state for the some time, so that if I want the process, that it will be enabled or it will be accessed easily by the parent child or the parent process. This says when the parent reaps, that is the parent deletes the terminated child, the kernel passes the child exit status to the parent and then discards the terminated process, at which point it chooses to exit. This says at the point when the parent reaps the child process terminates and removes from the list of the parent. A terminated process that has not yet been reaped is known as a zombie process. That is a terminated process that is not reaped. That is, exit function is used for terminating the process, but the parent does not reap the child process. That is known as the zombie process. If the parent process terminates without reaping its zombie children, that is, and now if there is a condition, then that there is a one process that is a zombie process, that is the parent process does not terminate or does not reap the child process, but instead or currently or suddenly the parent child also terminate without reaping the zombie children. The kernel arranges the init children or init process to reap them. Then it is a responsibility of the kernel to reap the child process. Why? It is not reaped by the parent, so it is reaped by the child process. The init process has a PID of 1 and it is created by the kernel during system initialization. Load running system such as cells or server should always reap their zombie children. So whenever operating system open the system or uses the system, so it always first of all check with the zombie process. If there is a zombie process and the parent is not available, so first of all the kernel reaps the zombie children even though they are not running, even though they are running. It depends on the kernel to kernel, it reaps the child function. A process waits for its children to terminate or stop by calling the wait PID function. Then wait PID function is used for the parent to for the parent that waits for the children to terminate or stop. So wait PID function, this is the example, that is this type.h, wait.h, there is a PID underscore t, wait PID. Then using the variable that is PID t, PID int status, int options. Returns PID of child if okay, 0 if not okay, that is hang, or 1 if on error. This says the wait PID function is complicated. That is, it is complicated. By default, when option equals to 0, VID or wait PID suspend execution of the calling function. That is, it will suspend for the calling function. It will suspend the execution of the calling function, that is a parent process, until a child process in its wait state. That is, until a child process gets its wait state terminates. If a process in the wait set is already terminated at the time of the call, then wait PID returns immediately. In either case, wait PID returns the PID of the terminated child that caused PID to return, and the terminated child is removed from the system. So this is how wait PID is used and how child will be removed. Next is determining the members of the wait set. That is how to determine the members of the wait set that is in the waiting state, or that is used by the, that is done by the using the command or using the function that is wait PID function. The members of the wait set are determined by the PID argument. So it is determined by the PID argument, and there are two conditions. If PID is greater than 0, then the wait set is the singleton child process whose process ID is equals to PID. If PID equals to -1, that is, if it is greater than 0, then it is a then the wait set is a singleton process whose or the singleton child process whose process ID is equals to PID. Then if it equals to -1, then the wait set consists of all of the parent child processes. The wait PID function also supports other kind of wait sets involving user Unix process group that we will not discuss. These are the two criteria that is used if it is greater than 0 and it is greater than or equals to -1. Then how to modify the default behavior? The default behavior can be modified. That is by default, that is a predefined behavior can also be modified by using the option, by setting the options to various combination of the WNO hang or the WUN tract constraint. That is, by using these two functions, by using these two comparison constraint, we can change the default behavior of the process by default behavior of the calling function or the call function. One is WNO hang. It returns immediately, or it returns immediately with the return value of 0 if none of the child process in the wait set has terminated yet. This is the condition that shows or that returns the process that returns the 0 value immediately if none of the child process, that is, if none of the or any child process in the wait set has terminated yet. That is, if it has not terminated yet, it will it will use or it will take the child process in the wait state and has been terminated yet. The default behavior suspends the calling function. That is, the default behavior suspends the calling function until a child terminates. This is used for the returning the immediately, or it is used in the case when you want to continue doing useful work while waiting for the child to terminate. That is, if the parent process is wait for the child to terminate, that is, it uses the behavior that is the WNO hang. In the same way, next constraint is that WUN track. It suspends the execution of the calling process until a process in the wait set becomes either terminated or stopped. That is, it suspends the execution of the parent process until the child process becomes either terminated or the stopped. This is your WUN tracked function. Then next is your combination of the both, that is WN hang, WUN track. It returns the immediately with the return value of 0 if none of the children is waiting for the parent process, that is the WNO hang process or hang function or WUN tracked function. Then how to change the exit status of a reap child? So these are the multiple functions that is used that I will discuss after taking a break. So let's take 5 to 10 minutes break and then come back starting with the topic, that is how to change the exit status of a reap child. What is a reap child? That is the child that is terminated and then reaped by the parent. So how to check the exit status? This will be checked by using various functions that I will discuss after the break. So let's take 5 to 10 minutes break and then come back starting with this topic. Next topic is your, let's start with the next topic, that is checking the exit status of the reaped file. That is how to check the status or how to check the exit status of a reaped child. That is the reaped child that is reaped by the parent. So how to check the exit status? If the status arguments is not null, the wait PID then encodes status information about the child that codes the return in the status argument. This says if the status argument, that is the status of the child, is non-null, that is not null, then the wait PID function encodes the or encoded the status information, that is the status information about the child that codes the return in the status argument. The wait.h, that is a header file, includes the file that defines several macros for interpreting the status arguments. That is for interpreting the various arguments, status argument. The wait.h includes the various several macros for defining the files. Then these are the multiple status registers that is used. One is WIF exit ED or exited. That is WIF exit status. That is, it returns a true if the child terminated normally. That is, if it is terminated normally, that is the reap condition, it terminated normally. Child is terminated normally via the call or the to exit or a return. That is, then the status is your VIF exited. Then W exit status, that is, it returns the exit status of a normally terminated child. The status is only defined if WIF exited returns true. That is, it returns the exit status of a normally terminated child. So first one says it returns a true if the child is terminated normally. Then next gives the exit status of a normally terminated child. The next is WIF signal, that is, it returns the true if the child process terminated because of a signal that was not called. That is, first of all says it returns when the child terminates normally. Then next one is that it returns a true if the child process terminated because of a signal is not approaching, or the signal of a or the signal is not caught, that is not approaching. Then next WTerm sig, that is returns the number of signals that the child process to terminate. The status is only defined if the WFI signal status return true. That is WTER MSIC returns the number of signals only that causes the process to terminate, and it is always returns returns the true that whenever the signal is caught by the whenever the VIF signal status is true. Then VIF stop, that always returns the 0 if the child that causes the return is currently stopped. That is, the child that is causing the return is normally stopped, then it returns the or gives the value as a true value. The next status is your WSTO PSIG, that returns the number of signals that the child to stop. That is the number of signals that is required to stop the child for executing, that is provided by the WSTO PSIG status. This status is only defined if the upper function, that is your WIFS stop, returns true. So these are the status registers that is available for a reef child, for a reef function. Then next is your error condition. That is, what is the error condition is in the wait PID. This says if the calling process has no children, that is there is no children of the calling process, that is parent has no child, then the wait PID returns -1. That is, if the parent process is all alone and it does not have a single child, then it does not have a children, then the PID returns the -1 and sets error number to the ECHILD. So it gives an error number, it sets the error number to the ECHILD. If the wait PID functions was interpreted by a signal, and then it returns -1 and sets error number to EINTR. That is, there are two conditions. If it returns -1, then set the error number to the ECHILD. If the wait PID functions was interpreted by the signal, then it returns -1 and set error number to the EINTR. So these are the two conditions that is used, that is what is PID or what is wait PID and how it returns the value. So first of all says it returns -1 and set the error number to the ECHILD, and it was interpreted by the signal, then it returns the -1 and then set the error number to the EINTR. This is an example that shows the various outcomes, that is int fork equals to 0. That is, check the condition. If the newly created process is equals to the 0, then printf or print the value A, else print the value B, and initialize or make the wait PID value equals to -1 if there is a null value or the 0 value. Otherwise print the C value. That is, there are three conditions, either print A, either print B, either print C. Then next is your wait function, that is similar to the wait PID, that is used for calculating the status of the wait, that is calling wait, that is ampersand status is equivalent to the calling wait PID, that is -1 status 0. So this is wait. There are three arguments used, that is -1, that is your status, that 0. In this there is only one argument used, that is ampersand status. Then these are the examples of using wait PID. This is the example for wait PID. This is again new example of wait PID. Then next process or the next topic for the process control is that how to put or putting the processes to the sleep. That is, how to put the different processes to the sleep mode. This says the sleep function suspend a process for a specified period of time. That is, the sleep function is used, or sleep function suspend the process or suspend a single process for a specified number of the or the specified period of the time. This gives an example, that is hash include unit UNI std.h, then unassigned or the unsigned int sleep, that is using the unsigned integer, and the variable name is your sleep, and the argument defined are also of unsigned, that is of int type, and the variable name is sec, that is your SCC seconds. Then this is the argument. This says sleep returns 0, that returns left to the sleep. Now sleep returns 0 if the requested amount of time has elapsed. The requested time of amount means, or amount of time means, the time that is required for the process to execute, that is your requested time. If that time is over, that time is elapsed, then the sleep returns the 0 value, and the number of seconds still left to sleep otherwise. That is the number of argument or the number of seconds still left to sleep otherwise. The latter case is possible if the sleep function returns prematurely. That is the lower case or the lower part, that is the seconds or the number of seconds still left to sleep, is possible if the sleep function returns prematurely because it was interpreted by a signal. We will discuss signal in detail in section number 5. We will discuss in next class, that is the tomorrow's class, how to use the sleep function and how to use the sleep function if the requested time is 0 or elapsed. Another function that will be find useful is the pause function. That is, one is your sleep function, one is your pause function, which puts the calling function to sleep until a signal is received by the process. That puts the calling function, that puts the parent process or the parent function to sleep until a signal is received by the process. That is, until a signal is not provided by the process, then the parent process is not active and is not participated in the execution of the process. This is the example, that is hash include unist.h, that is a header file that includes all the file. Then use a function, that is a pause function, that is of int type. This is the example that write a wrapper function for the sleep known as snooze with the following interface. So these are the function name, function argument, type, all are defined. Then next part is how to load and run the program. That is also a part of the process control for controlling the process. The next topic is your loading and running the program. That is how to load and how to run the program. That is done by the function, that is defined by the function, that is used by the function, that is known as the execc VE, that is your executable file, that is executable function, or the execc VE function loads and runs a new program in the context of the current process. That is, if there is a current process is running, so execv function is used to load and run a new program in the file in the context of the current process. Suppose my process is of contains 4 instructions. Then it is used, or the executable function is used to load and runs a new program in the context of the current process. That is, if current is running, then it will bring the new process or load the new process for executing the next process. Suppose my OS operating system executes 4 processes, that is P1, P2, P3, P4. Then suppose the currently P1 is executing. Then P1 is executing. Then for the next part, that is for P2 part, it is the responsibility of the execve function that loads and runs the new program, that is your next program, next file, next process, that is your P5 process, to load and run the execution part. This is the example that shows hash include execve constant variable, file name, constant char, argv, constant char, envelope, does not return if OK, returns -1 or error. And then next point says the execc VE function loads and runs the executable object file name with the argument list argv. This is one of the most important line, that is the executable VE function, that is the execc VE function loads and runs the executable object file name with the argument list. That is, it loads with the or runs the executable object file with the argument list name, that is known as the argv. and the environment variable list, that is envp. So these are the two functions that is used with the executable function that loads and runs the executable object file, that is argv and envp. One is your argument v, one is your environment p. execv function returns to the calling program only if there is any error, such as not being able to find file name. So it returns the cursor back to the calling function if and only if there is any error. For example, not being able to find the file name. So unlike fork, which is called once but returned twice, exe is called once and never returns. Or that is, it is called only once but never returns any argument, never returns any result. This is the diagram that shows. This says the argument list is represented by the data structure that is shown in the figure 19. The argv variable points to the null pointed array of the pointers, each of which is used So this is the organization of argument list that is represented by the data structure. That is how argument list is represented. That is represented by the data structure. So one is argv function is used, then argv function used with the array, then argv 0, 1 up to argc minus 1, and at last there is a null character, there is a null value. Then next point says at argv there is a ls function, that is a listing function. At argv there is a -lt function. At argc minus 1 there is a root directory that starts with the user, that is user, and then include. This is the organization of the environment variable. Before this is the organization of the argv variable or argc, that is an argument list. Now there is organization of the environment variable, that is envp, that is your environment variable. So first of all there is a envp, that is environment variable, then envp blank, that is of array, that at 0 location, that is index number is 0, then 1, then envp n minus 1. Then there is a null character, that is your null values. In the same way, envp0, at envp0 pwd, that is your print working directory, equals to, that is what is the directory, where is the cursor, that is beyond the or prior to the usr, and then there is a draw, that is a droh. Then next is your envp, that is your at the first location there is a printer, that is your iron. Then environment n minus 1, that is usr, equals to draw, that is what is the username, it gives the username. By convention, argv0 is the name of the executable object file. So this says at the argv0 is the name of the executable file. The list of the environment variable is represented by the similar data structure in the figure 20. The same way in argv0 there is a name of the argument variable, name of the executable object file, but envp0 there is a print working directory, that is your location of the ID. Next point says the envp variable points to a null terminated array of pointers to the environment variable string, each of which is a name value pair of the form, that is name equals to value. Next point says after execve loads file name, that is once execve loads the file name, it calls the startup code, that is your starting phase, which sets up the stack and passes the control to the main routine. That is, first of all, a stack is prepared and then passes the control to the main routine of the new program. Main routine of the new program means a newly built process that is built by the fork process. We set up the stack and the passes the control to the main routine of the new program of the form, that is int main. So sorry, int main, their argument used one is int argc, then char argv, then char environment variables, or equivalently int main, int argc, char argv, char environment variable, that is your array variable. Next point says, when the main begins executing in a 32-bit Linux processor, the user stack has the organization shown in the figure 21.